Usually when we talk about a medical diagnosis, um, there's this expectation of precision, right? It's almost like engineering. You break your arm, the X-ray shows that jagged white line,
Yeah.
and the doctor just points at the screen and says, well, there it is. That's the problem.
Right. Yeah, it's binary. It's visible. And psychologically, I think that's very comforting for us. We like complex systems to be easily categorized into, broken or functioning.
Exactly. But if you're staring down a massive cloud architecture meeting on Monday morning, you know that the X-ray analogy just completely falls apart when it comes to enterprise databases.
Yeah.
I mean, you step into the world of migrating a legacy database to the cloud, and suddenly you aren't just looking at an X-ray. You are essentially being asked to perform open-heart surgery on a patient while they are, like, actively running a marathon.
That is a fantastic analogy.
Because you can't just stop their heart, right? The business has to keep running. The users are still querying the system, buying products, updating records.
Right. That is the perfect way to frame it, because the underlying reality of database migration is that it is this incredibly high-stakes, high-toil environment.
And that's exactly what we're going to unpack today for you. Welcome to this custom-tailored deep dive. If you're looking for a shortcut to mastering complex cloud architecture without the information overload, you are in the right place. We have a set of incredibly dense, highly practical notes titled PCDBE04 DMS Spanner.
Which is quite a title.
Yeah, it is. But our mission today is to dig into the raw mechanics of how massive organizations move their most precious asset, their data, into the Google Cloud. We're going to look at the strict, sometimes punishing prerequisites of native cloud migration tools.
Mm-hmm.
We're going to see why the holy grail of zero downtime is just an absolute myth. And finally, what happens when an organization outgrows standard relational databases entirely and shifts to Google Cloud Spanner, which is a system that handles over 2 billion requests every single second.
Which requires a total paradigm shift. I mean, it literally forces seasoned database engineers to unlearn decades of standard habits. Wow.
But, before we get to the planetary scale of Spanner, we really need to start with that high toil reality you just mentioned a minute ago.
Right. Let's talk about that word toil, because the notes use it very specifically to describe database migrations. They call them challenging, time-consuming, and high toil. If the cloud is supposed to be this magical, automated wonderland we always hear about, why is just getting the data there still considered manual labor?
Well, in the engineering world, especially in site reliability engineering, or SRE, toil doesn't just mean hard work.
Right.
Toil refers to a very specific kind of work. It's manual, it's repetitive, it's tactical, it's completely devoid of enduring value, and it scales linearly as the service grows. So migrating a massive enterprise database isn't just clicking a copy to cloud button.
If only it were that easy.
Exactly.
Mm-hmm.
You are dealing with incredibly complex mapping dependencies, subtle variations in database engines, and just the terrifying prospect of moving mission-critical infrastructure at scale. Right, because if you are moving from, say, an on-premises Oracle database to a PostgreSQL instance in the cloud, you aren't just moving data. You are translating the fundamental language and structure of the data while it's in motion.
Yes, exactly. And to understand why so many of these migrations fail, you have to realize it is rarely just a technology problem.
Really?
Yeah, I mean, the underlying technology, the network pipes, the migration software, it usually functions exactly as designed. What actually brings migration to its knees is poor organizational planning, a total misunderstanding of how deeply entangled the applications are, or honestly just picking the wrong application to move first.
Which brings us to the first massive hurdle. If this process is as risky as marathon open-heart surgery, how do you even pick the first patient? The notes emphasize a golden rule here, and I'll quote it. Don't choose a mission-critical app where the risk is too great.
Right.
But, okay, let's unpack this. If we aren't moving the important stuff, what's the point? How do you prove the value?
It's a great question. It's all about finding a very specific sweet spot for your first migration. You have to carefully balance business value against operational risk.
Okay.
So imagine a hypothetical company. Let's call them Globex Retail.
Classics.
Right. They have a massive on-premises data center. They want to move to Google Cloud. The CIO points to their core e-commerce transaction database, the system that processes every single credit card swipe, and says, move that first to prove the cloud works.
Oh, boy. That sounds like a resume-generating event waiting to happen.
Exactly.
I mean, if that database goes offline for 2 days because the team is still, learning how cloud networking functions, The company effectively goes bankrupt.
The risk is completely apocalyptic. So
Yeah.
the engineering team, naturally, they push back and say, well, let's move the database that tracks the cafeteria lunch menu instead.
Right, zero risk, but also zero reward.
Yeah.
Management won't care if it works because it provides no real business value.
Sure.
It doesn't prove the cloud can actually handle enterprise workloads.
Precisely. So you have to find that middle ground. Maybe Globex Retail has a customer analytics application. It provides real, tangible business value, like the marketing team uses it every day to optimize campaigns.
Okay, so it matters.
It matters, yes, but it's not in the critical path for revenue. If it goes down for 4 hours on a Tuesday because of a migration hiccup, the company loses some internal productivity, but no customers notice, and revenue doesn't stop. That is your ideal first candidate.
But, looking at the notes, they also bring in this deeply human element here, which I found really surprising for a technical architecture document. They specify that you need to consider the development and operations teams themselves. It says you should choose teams with Google Cloud knowledge, or at least teams motivated to use it.
Oh, that is the single most overlooked factor by leadership, without a doubt. Oh, absolutely. They look at a spreadsheet of applications, find that sweet spot analytics app, and say, migrate that one. But if the team managing that app is deeply entrenched in their on-premises ways and actively resistant to learning cloud architecture, every single step of the migration will be a brutal political uphill battle.
So you actively seek out the early adopters, like the engineers who are already reading the Google Cloud documentation in their spare time.
Yes, exactly. You want your first migration to be a quick, undeniable win. Motivation and enthusiasm can overcome a tremendous amount of technical friction. If the team actually wants to be in GCP, they will figure out the roadblocks.
That makes a lot of sense. Beyond the human element, though, there are hard technical constraints listed for choosing that first app. Dependencies, for instance. The text says, as dependencies increase, migration becomes more difficult.
Yeah, think about it this way. If that analytics application we mentioned earlier has to talk to 15 other internal databases just to generate a single report, you have a massive problem.
Because of the network distance.
Exactly. If you move the analytics database to the cloud, but leave the other 15 on premises, you've just introduced massive network latency. Every single query now has to travel back and forth from the cloud to your local data center 15 times. The app will just grind to a halt.
So you're looking for an app that is relatively isolated, sort of a lone wolf in the architecture.
Or you have to commit to moving all 16 databases simultaneously, which massively inflates the risk and the scope of the project. So yeah, isolation is key for early migrations.
The notes also flag licensing and compliance, which seems like a non-technical issue that could completely derail a project.
You would be stunned by how many migrations get 80% of the way through the pipeline, only for the legal department to slam the brakes because the legacy software license specifically prohibits cloud deployment without, like, a multi-million-dollar true-up fee.
Wow. Okay, so let's say Globex Retail threads the needle perfectly. They find an isolated analytics app. The marketing team cares about it but won't die without it. The DevOps team is thrilled to learn GCP, and the licenses are clear.
Perfect scenario.
Right. They are ready. The target environment is provisioned. But eventually, you have to actually cut the cord. You have to turn the old on-premises database off and the new cloud database on. This is where we hit the most terrifying phase of the whole endeavor.
The cutover window.
Yeah. And the notes have a specific phrase here that I think shatters a lot of marketing illusions. Quote, zero downtime, practically unachievable. Wait, really? Isn't the whole pitch of the modern cloud that it's this magical, seamless fabric? We can't just float data into the sky without anyone noticing?
It's a harsh reality check, isn't it?
Definitely.
What's fascinating here is that engineering, at its core, is a constant negotiation with the laws of physics, specifically the physics of data gravity.
Data gravity, meaning what the data physically takes up space and time to move?
Exactly. Data has mass, metaphorically speaking. Moving 10 terabytes of data over a fiber optic cable takes a fixed amount of time. You cannot change the speed of light. So if you want a migration to be completely simple and foolproof, say, just shutting the system down, exporting a massive file, uploading it, and importing it, you're going to suffer massive downtime.
Because while you were spending 10 hours copying that file over the network, the database has to be locked. I mean, if you let users keep adding data to the old system while the copy is happening, your new cloud database is instantly out of date the moment it turns on.
Right. So the sources present downtime as a spectrum. On the far left, you have the simplest approach with the most downtime, which is scheduled maintenance. You put up a banner that says system offline for the weekend.
Which nobody wants to see.
No, nobody. It's technically simple, but commercially devastating.
So then you move along the spectrum to continuous replication, which we'll get into the mechanics of shortly, where the downtime is much shorter, but the setup is harder. And then on the far right, for the absolute least amount of downtime, the notes list split reading and writing and data access microservices. But how does a microservice actually reduce downtime?
Well, this is where you trade downtime for extreme architectural complexity.
Okay.
If zero downtime is a myth, you aim for a window so small the user doesn't even notice maybe seconds or milliseconds. To do that, using a microservice, you essentially build a middleman.
A middleman between the application and the database?
Yes, exactly. You rewrite a piece of your application so that instead of talking directly to the old database, it talks to this new custom data access microservice. This microservice intercepts every single write request, every new customer, every new order.
Oh, wow.
Yeah, and then it performs double-entry bookkeeping. It writes the exact same data to the old on-premises database and the new cloud database simultaneously.
Okay, I see where this is going. The application doesn't even know it's migrating. It just hands the data to the middleman, and the middleman ensures both databases stay perfectly in sync.
Exactly. And once you have imported all the historical data and the microservice is keeping the live data perfectly synchronized, you simply flip a switch in the microservice configuration. You tell it, stop writing to the old database, only write to the cloud. Boom. Your downtime was literally just the milliseconds it took the microservice to reload its configuration.
That sounds amazing, but wait, I have to push back here. Writing a custom microservice that can handle intercepting the entire read and write load of an enterprise application without introducing massive latency. I mean, that is a massive software development project all on its own, isn't it?
You've hit the nail on the head. That is the trade-off. To avoid a weekend of downtime, you might spend 6 months of engineering time building, testing, and deploying that microservice perfectly. And if that microservice crashes under load, your entire system goes offline anyway.
So to manage all these trade-offs, whether you are doing a simple weekend maintenance window or a complex microservice double write, you really need a framework. The sources outline a strict 5-step database migration methodology. Step 1 is analysis. Step 2 is tool selection. But step 3 is where the notes really dig their heels in. It's the proof of concept.
And notice the exact wording they use there. It doesn't just say run a test. It says implement production equivalent database migration and replication.
Yeah, I saw that. But if we're just doing a proof of concept of POC, why does it have to be full production scale? Isn't the point of a POC to just test the waters on a small sample to see if the tool even works?
This is exactly where so many architects get burned.
Really?
Oh, constantly. They spin up a tiny 1 gigabyte sandbox database with 0 active users. They connect to their migration tool, click a button, and the data moves in 3 seconds. They declare the POC a massive success, and they sign the contract.
And then they try it on the real thing.
Right. They try to migrate a 20 terabyte production environment with thousands of concurrent users hammering the system with updates.
Oh, no.
And the migration tool, which worked perfectly in the sandbox, completely collapses. The replication pipeline backs up, the CPU spikes to 100%, and the system crashes. Your proof of concept must mirror production volume, production network latency, and production transactional activity. If it doesn't, it's not a proof of concept, it's a hallucination.
A hallucination. That is a phenomenal warning. So if your PPC actually survives the gauntlet, you move to step 4, which is the actual execution of the migration.
Yeah.
But then there is step 5, fallback. The notes say, quote, be ready for fallback to source database in case of failure. Test fallback as well.
Yes. And I cannot emphasize the importance of this step enough. Let's say you do the cutover. The new cloud database is live. But an hour later, something goes catastrophically wrong. The latency is so bad the application is timing out, or worse, the cloud database is silently corrupting data due to a character encoding mismatch. What do you do?
If you haven't planned for it, you panic.
You panic, and your business is hemorrhaging money. You must have a rigorously tested fallback plan. You need to know the exact commands to point the application back to the old on-premises database. And even more complex, you need a strategy for what to do with the data that was written to the cloud database during that 1 hour it was live.
Right, because you can't just lose those orders.
Exactly. How do you extract those new orders and patch them back into the old system? If you haven't tested the fallback, you aren't ready to migrate.
This brings us to the actual mechanics of the cutover itself. When we finally execute this, what actually happens? The notes detail the process of switching clients, and it involves three distinct phases. First, closing connections to the source database.
You have to stop the bleeding. You sever the application's ability to talk to the database so no net new data can enter the system.
Okay, then there is a phase called draining. It says, migrate remaining changes. What exactly is draining?
So imagine the database is a massive sink, and the network connection is the faucet. Closing the connections is turning off the faucet, but there's still water swirling around the drain.
The transactions that were already happening.
Exactly. Those are the transactions that were already in flight queries that were halfway executed when you pulled the plug. Draining is the agonizing wait. You have to let those final transactions finish processing and replicate over to the new cloud environment. If you cut the pipe before it drains, you lose data.
And once it's totally drained, that final drop of water hits the new database. Phase 3 is opening the new connections to the target. So that draining phase, that is the downtime.
Exactly. Even in a highly optimized continuous replication scenario, that draining phase takes some non-zero amount of time. It might be 10 seconds, it might be 10 minutes. But that is why zero downtime is a myth.
Okay, so we've mapped out the methodology. But before we actually open the floodgates to the new cloud database and let the application start writing live customer data to it, we have to know for an absolute certainty that the new environment is safe. Right? We have to prove that the data arrives intact and that the application can read it. Which brings us to the triad of testing.
Yes. Testing is the only thing standing between a successful launch and a total disaster.
The source material is very clear here, so if you're listening, pay close attention to this. There is a real-world architectural trap hidden in how teams test. So look at how they differentiate these three phases. Let's start at the micro level with unit tests. The notes define this as testing individual functions, properties, stored procedures, triggers, etc.
Right. So in a database context, unit testing is about zooming in on the smallest atomic pieces of logic. Let's say your database has a stored procedure like a piece of code living inside the database that calculates local sales tax based on a zip code. A unit test asks one simple question. Does this isolated piece of code still calculate the tax correctly in the new Google Cloud environment?
So you're just feeding it a zip code and checking the math. You aren't testing if the user interface works or anything.
Exactly. You test it in total isolation. If it passes, you know the internal gears of the database survived the move.
But the notes imply that unit testing, a stored procedure in a vacuum, is incredibly dangerous if you stop there.
Right.
Which leads to the second layer, integration tests. The definition is ensure that different components work together. Clients can use their services, services can use their databases. Isn't integration testing basically just unit testing two things at the same time?
No, actually, and that misconception is exactly why migrations fail post-launch. An integration test validates the connective tissue between systems. You can have a unit test pass with flying colors like the tax calculator works perfectly inside Cloud SQL.
Right.
But if the integration test fails, it might mean the web server in London physically cannot reach the database in Frankfurt because of a firewall rule.
Oh, wow. Okay.
Or it might mean the identity and access management, the IAM rules, weren't configured correctly, so the application is being denied permission to authenticate. The engine works, the transmission works, but if you don't bolt them together correctly, the car doesn't move. Integration tests prove the plumbing works in a distributed cloud environment.
So we have the internal logic tested, we have the network plumbing tested. What is the third piece? Regression tests. The notes say, ensure that the new platform is consistent with the older one. New functionality does not break other older code. My understanding of regression testing has always just been, making sure we didn't accidentally break something that worked yesterday. Is it really that simple?
Conceptually, yes. But in a database migration, it takes on a much heavier meaning, especially regarding performance. Because you are rarely doing a perfectly identical move. Maybe you are moving from an on-premises PostgreSQL version 11 running on massive proprietary hardware to PostgreSQL version 14 running on virtualized Google Compute Engine infrastructure. A proper regression test takes a massive suite of historical queries, thousands of complex joins, and reports that worked perfectly last week, and runs them against the new cloud database.
So you're trying to see if the new version of Postgres handles the query differently.
Exactly. It's about establishing a performance baseline. If a complex marketing report used to take 2 seconds to generate on-premises, but now takes 45 seconds in the cloud because the new database engine handles indexing slightly differently, that is a performance regression. It technically works, but it will destroy the user experience. Regression testing proves that the entire system behaves identically or better than the legacy system under real-world conditions.
That makes perfect sense. So we have our safety nets built. We understand the risks. It is finally time to look at how we physically move the heavy machinery over the wire. Let's look at the actual tactics and tools from brute force to elegant synchronization.
This is where the theoretical planning meets hard engineering.
The sources outline a few different approaches, and they really range in sophistication. The first one listed is lift and shift migrations based on OS images. The examples given are VMware.vmdk files and Microsoft.vhd formats. It says a compute engine VM, or GCE, is created to run the import and conversion. There's even an example of exporting an AMI to an S3 bucket in AWS and importing it to Google. We're throwing around a lot of acronyms here.
Yeah, let's demystify those. GCE is Google Compute Engine. It just means a basic virtual machine running in the cloud. AMI, VMDK, VHD, these are all just different file formats for taking a snapshot of an entire hard drive.
So lift and shift literally means taking a digital photograph of the entire physical server.
Basically, yes. You aren't migrating the data out of the database. You are turning off the server, creating a massive file that contains the operating system, the database software, the security patches, and the data, and you are just booting that exact same image up on a virtual machine in Google's data center.
That seems incredibly brute force compared to the elegant microservice architectures we were just discussing.
It is the bluntest instrument available. Organizations usually do this when they have a literal gun to their head, like their physical data center lease expires next month and they just need to get out fast. The problem is, you take all your technical debt with you. If your operating system was bloated and misconfigured on premises, it will be bloated and misconfigured in the cloud. And you aren't gaining the benefits of a managed service. You still have to patch the OS yourself.
Right. Okay, so if we want to move up the sophistication ladder, we look at the next tactic, backup and restore. The notes call this the simplest way to migrate a database. But they include a really deep architectural tactic here, specifically for massive databases to minimize that downtime window we talked about. They suggest using differential backups.
Oh, this is a classic database administrator survival tactic.
Let me read the 3 steps they outline because I want you to walk me through exactly how an engineering team executes this over a weekend. Step 1. Start with full backup and restore it to target. Step 2. Move to differential backups and restore at regular intervals. Step 3. Finally, schedule maintenance on source, take last backup, and restore on target.
Okay, let's play this out. Let's go back to Globex Retail.
Yep.
They have a 10 terabyte database. If they take the system offline to copy 10 terabytes over the network, it might take 48 hours. The business cannot be down for 48 hours.
Right, the data gravity issue.
So they cheat the system. On Monday morning, while the system is live and users are active, the engineers trigger a full backup. It starts creating a massive 10 terabyte file. It takes hours to generate, and then they slowly start transferring it to Google Cloud. By the time it finally finishes copying and restoring in the cloud on Wednesday morning, the data is already 48 hours out of date.
Because users were still buying things on Monday and Tuesday?
Exactly. So on Wednesday, the engineers take a differential backup. A differential backup only looks for the blocks of data that have changed since Monday morning. Instead of 10 terabytes, it's maybe only 500 gigabytes.
Oh, so that transfers much faster.
Right. They copy that 500 gigabyte file over and apply it on top of the cloud database. Now, the cloud database is only slightly behind. They do this again on Thursday. The file is smaller. They do it again on Friday.
But wait, if we are continually running these backup processes while the system is live, doesn't that put a massive CPU and disk I/O strain on the on-premises database right when users are trying to use it?
It absolutely does, and that is a critical operational risk. You have to tune the backup software to run at a lower priority or run the differentials during the middle of the night. It's a delicate balancing act. But if you manage the performance impact, you get to Friday night.
The cutover weekend.
Yes.
Yeah.
By Friday night, they take one more differential backup. Now, the cloud database is only 1 hour behind the live system. At 2:20 a.m. on Saturday, they announce the scheduled maintenance window. They lock the users out, they close the connections and drain the database, just like we talked about earlier.
The system is officially down.
The system is down. They take one final, tiny differential backup of just that last hour of activity. It might only be 5 gigabytes. It copies over the network in 2 minutes. They apply it. The on-premises database and the cloud database are now mathematically identical. They open the connections to the cloud and the system is back online. They moved 10 terabytes of data, but the actual downtime for the business was maybe 15 minutes.
Wow. That is a brilliant piece of engineering sleight of hand.
It really is.
But what if even 15 minutes of downtime is unacceptable? The next tactic the notes provide is replication-based migrations. And there is a real-world scenario outlined here for minimizing downtime using what they call an external server.
This is a highly specific, very powerful networking pattern on Google Cloud, specifically for moving to a fully managed database like Cloud SQL.
The scenario reads like this. Your customer is running a MySQL database on-premises with read replicas. The nightly incremental backups are expensive and add maintenance overhead. You want to follow Google recommended practices to migrate the database to Google Cloud, and you need to ensure minimal downtime. The correct architectural solution provided is create an external replica and use Cloud SQL to synchronize the data to the replica. How does that actually work under the hood?
It works by using the database's native ability to replicate itself, but inverting the control. Normally, if you set up replication, the master database has to be heavily configured. You have to tell it, hey, I have a new server over here in this IP address. Please push data to it.
Which requires changing configurations on the live production on-premises database, which administrators absolutely hate doing.
Exactly. So instead, you use the Cloud SQL external server feature. You go into Google Cloud, you spin up a Cloud SQL instance, and you give it the IP address and credentials of your on-premises database. Cloud SQL then reaches out across the internet, usually through a secure VPN tunnel or Google Cloud Interconnect, and essentially knocks on the door of your on-premises database.
What kind of networking hurdles are we talking about there, though?
Oh, massive ones. To make this work, the network engineers have to open specific ports on the corporate firewall to allow Google's IP ranges to talk to the internal data center. You might have to configure VPC peering or set up a dedicated interconnect circuit. But once the network pipe is open, the Cloud SQL instance says to the on-premises database, "Hi, I'm just a normal read replica. Please send me your transaction logs."
So the on-premises database doesn't even know it's being migrated to a managed cloud service. It just thinks it has a new server locally asking for updates.
Precisely. Cloud SQL handles all the heavy lifting of pulling the initial data load, and then it just sits there, silently digesting every update in near real time. It's a perfect mirror. Then, during a tiny downtime window, you sever the VPN connection, you go into the Google Cloud console and click Promote Replica. Cloud SQL instantly reconfigures itself to become a standalone primary master database. You point your applications to it, and you have just stealth migrated an enterprise database to a fully managed service.
That is incredibly elegant. But as with all things in tech, there are always hidden traps, right?
Oh, always.
Everything we've talked about with managed services brings us to our next major topic. What if we want to use Google's highly touted Native Database Migration Service, or DMS? Because according to our sources, DMS comes with some very strict, uncompromising rules based on the laws of computer science, particularly if you are dealing with PostgreSQL.
Yeah, DMS is a phenomenal tool. It automates so much of the serverless data movement and monitoring we just discussed. But it is not magic. It relies on the fundamental mechanics of how database engines actually record data.
And the notes practically scream at the reader to pay attention to these mechanics. They outline strict prerequisites for migrating a PostgreSQL database from on-premises or from AWS into Cloud SQL using DMS. The first major prerequisite is something called bilogical.
Yes.
The notes say, install the bilogical package on the source instance and make sure that it's included in the shared preload libraries variable. What exactly is this package doing?
Well, Blockological is a PostgreSQL extension that enables logical replication. To really understand that, you have to understand a concept called CDC, or Change Data Capture.
Okay, let's break that down. What is CDC?
CDC is essentially a listener. Think of it like a security camera watching the database. But it doesn't watch the data tables themselves. It watches the database's internal diary. In PostgreSQL, that diary is called the WAL, the write-ahead log.
Oh, the notes mention wall. They say you have to set the configuration variable wall level equals logical.
Right. Every time a user inserts a row or updates a record, PostgreSQL writes that action into the WAL file before it permanently saves the data to the hard drive. It's a safety mechanism for crash recovery. Change data capture tools like DMS read that WAL file to see exactly what changed in real time. But a standard WAL file is written in a binary format that only the local database engine understands. It's just gibberish to an external system.
So setting wall level equals logical and installing pendylogical acts as a translator.
Exactly. It tells PostgreSQL to add extra human-readable metadata to the log file, and Pegalogical translates those internal binary changes into a structured stream of logical commands like update table X, set column Y to Z, that DMS can actually parse and send across the network to the new cloud database.
Okay, the translator aspect makes sense, but the next prerequisite is the one that really caught my eye. Let's say I'm a developer. I've set up my wall levels. I installed my extensions. I run this enterprise-grade Google migration tool, and it just ignores some of my tables. The notes explicitly state, tables without primary keys are not automatically created and migrated by database migration service. Why does this tool just refuse to move tables without primary keys? That seems like a broken product.
I completely understand why developers find that frustrating. It feels like the tool is just being lazy. But this goes back to the mechanics of that change data capture stream we just talked about.
Walk me through the mechanism. Why does it physically need a primary key?
Let's imagine you have a massive table of customer orders. Someone goes into the on-premises database and updates the shipping address for a specific order. The WAL file records the change, Pclogical translates it, and DMS captures a message that says, update the shipping address to 123 Main Street. It sends that message to the target database in the cloud. The target database receives the message and says, great, I will update the address to 123 Main Street. But for which order?
Oh, I see.
Yeah, if the table has a primary key, say a unique order ID of 5555, the message from DMS is update the address for order ID 555. The target database instantly finds that exact row and updates it safely. But if the table has no primary key, there is no unique identifier. The CDC stream knows a row changed, but it has no safe, guaranteed way to tell the target database which row changed among potentially millions of identical-looking rows.
It's like a blindfolded postman trying to deliver a letter in a town where none of the houses have numbers. He knows he has mail for John Smith, but there are 50 John Smiths on the street, so he just throws his hands up.
That is exactly it. If DMS tried to guess, it might accidentally overwrite 1,000 rows, irreparably corrupting your data. So rather than risk data destruction, DMS has a hard-coded safety mechanism. It simply refuses to replicate tables without primary keys. It is a limitation born out of mathematical necessity.
That completely reframes it from a bug to a critical safety feature. The notes also list a few things DMS explicitly does not do during migration. It doesn't move tables with large objects, like if you are storing massive video files directly in the database, you have to use a manual dump tool. Why?
Because streaming a 4 GB video file through a logical replication pipeline designed for tiny text updates will completely clog the network pipes and crash the CDC process.
Makes sense. It also says DMS doesn't automatically move database users or ACL's access control lists. You have to recreate the user accounts on the target manually. And it doesn't automatically create high availability configurations or read replicas during the initial migration.
Which is a very intentional design choice by Google. When you are moving terabytes of data across the internet, you want the pipeline to be as simple and unburdened as possible. If the cloud database is trying to synchronize data to a secondary high availability node at the exact same moment it's trying to ingest the massive initial load from the migration, the disk I/O will bottleneck. The philosophy is, get the data across the wire safely to a single node first. Once it's fully synced, then turn on the fancy cloud features like HA.
Speaking of knowing when it's fully synced, I love the verification tip they provide for DMS. After all this talk of WAL files and CDC streams, the recommended verification method is beautifully low-tech. It says the most reliable way to determine that all data has been migrated is to make one last change manually on one of the source databases and wait for that change to appear in the corresponding target database.
It's the ultimate, undeniable end-to-end integration test.
You literally just insert a dummy row that says migration test on the on-premises server, switch tabs to the Google Cloud Console, and wait 3 seconds. If it pops up, you know the wall is working, the network is open, DMS is running, and the target is accepting writes.
Exactly. It bypasses all the complex monitoring dashboards. If the data flows, the pipe is open.
So everything we've talked about up to this point is predicated on migrating to a standard relational database. We're talking about moving a traditional database from a server in your basement to a server managed by Google. But what happens when an organization reaches a scale where standard relational databases fundamentally break down? What if you need a database that spans the entire globe, and a single master server simply cannot handle the traffic physics? That brings us to our final and frankly most architecturally mind-bending segment, the spanner paradigm shift.
Yeah, we are leaving the realm of standard architecture now. This is where the physics of data gravity are challenged by sheer engineering force.
The notes introduce Cloud Spanner with some statistics that I genuinely had to read 3 times. The scale is almost incomprehensible. Spanner processes over 2 billion requests per second at peak. Spanner has more than 6 exabytes of data under management.
Let's contextualize that for a moment. An exabyte is 1 billion gigabytes.
Wow.
Spanner is managing 6 of those, and 2 billion requests a second. I mean, if you tried to push that level of transactional traffic through a traditional Oracle or PostgreSQL cluster, the hardware would literally melt. It exceeds the bounds of standard computing.
And yet, the features listed in the notes read like a database engineer's impossible wish list. It is horizontally scalable. It's fully managed with a 99.999% uptime SLA. It says there is no maintenance downtime, no software patching, upgrades, index rebuilds, or resharding. And it offers zero-touch global replication with strong external consistency.
And that phrase, strong external consistency, is the true paradox of Spanner, and it's really what makes it Google's crown jewel.
Explain that paradox for us.
Historically, in computer science, you had to make a choice. If you wanted ACID transactions and standard SQL schemas, meaning mathematical guarantees that your bank transfer won't get lost, you used a relational database like MySQL. But relational databases only scale vertically. You just have to keep buying a bigger, more expensive server.
Until you run out of bigger servers.
Right. If you needed to scale horizontally across thousands of cheap servers, you had to use a NoSQL database. But the trade-off for NoSQL was losing that strong consistency. You couldn't guarantee that a user in Tokyo and a user in London were seeing the exact same data at the exact same millisecond. Spanner solves the paradox. It offers the infinite horizontal scaling of NoSQL, but keeps the rigorous mathematical consistency and SQL interface of a traditional relational database globally.
Okay, I have to push back here. It sounds too good to be true. And reading further into the notes, there is a massive architectural catch. The notes explicitly contrast traditional RDBMS with Cloud Spanner. Under the traditional column, it says the database is in control of value constraints, data verification with triggers and stored procedures, and user access. But under Spanner, it says business logic in the application layer. Why? Triggers are incredibly efficient because they live right next to the data. Why is Spanner forcing us to move all that logic out to a slower application layer?
Because of the physics of global distribution. To understand why Spanner forces developers to unlearn decades of standard database habits, we have to look at how a trigger actually executes.
Let's walk through an example.
Imagine you have a legacy, vertically scaled database. You write a trigger that says, before a user can insert an order for a pair of sneakers, run a complex stored procedure to check the inventory levels in all 5 of our warehouses, calculate the shipping latency, and reserve the stock. Because all the data and the trigger are sitting on the exact same physical hard drive in the exact same server rack, that calculation happens in a fraction of a millisecond. The database acts as the ultimate brain, enforcing all the business rules.
But Spanner isn't one machine.
Spanner is sharded across thousands of machines globally. A single Spanner database might have pieces of its data living in Tokyo, London, and Iowa simultaneously.
So if you put that complex sneaker inventory trigger inside Spanner,
it creates a massive system-halting bottleneck. Let's say a user in London tries to buy the last pair of sneakers, and at the exact same millisecond, a user in Tokyo tries to buy them. If the complex business logic lived inside the database layer, Spanner would have to halt the transaction, lock the table, send internal network messages across the ocean via fiber optic cables, wait for the responses from the Tokyo shard, run the calculation, and then proceed.
And you obviously cannot process 2 billion requests a second if every transaction is waiting for the speed of light to travel across the Atlantic Ocean just to run a stored procedure.
Exactly. To achieve 99.999% uptime, zero-touch global replication, and unlimited scale, the database itself has to be incredibly lean. It has to focus its massive computing power on one thing and one thing only: storing and retrieving data with absolute globally synchronized consistency.
So it strips away all the smart features developers are used to relying on.
Yes. The notes detail exactly what minimal features it retains. Spanner only keeps the absolute bare minimum constraints necessary to prevent the literal structure of the tables from collapsing. Not null constraints, foreign key constraints to ensure relational mapping, and unique indexes. That is it.
So the database is essentially saying, I will ensure this field isn't empty, and I will ensure this ID matches a real user. But I am absolutely not doing your complex business math for you.
Right. It forces the developers to completely refactor their code. You have to take all those triggers and store procedures you wrote in the 1990s, delete them from the database, and rewrite them as distributed microservices in Java, Python, or Go. The application layer now determines what is valid. The application intercepts the user in London, runs the inventory check using a fast in-memory cache, verifies the business rules, and then hands a perfectly formed, pre-validated row of data to Spanner.
And Spanner just rapidly writes it to disk and replicates it globally without having to think about it.
Exactly. You are moving from an architecture where the database is a micromanager verifying every piece of math to an architecture where the application layer acts as a team of highly trained specialists, and the database is just an incredibly fast, infinitely large, globally synchronized filing cabinet.
That is a staggering realization for an engineer preparing for a migration. When you move to a system like Spanner, migration isn't just about moving data from server A to server B. It is a fundamental refactoring of how your software operates. You have to abandon the monolithic database as a brain mindset entirely.
It's a huge mental leap.
Well, we have covered an incredible amount of deeply technical ground today on our mission to unpack these PCDBE architecture notes. Let's do a quick recap of the journey we've been on. We started by confronting the harsh, high-toil reality of migrations. We learned that the most important decision you make isn't always the tooling. It's the political and operational decision of picking a low-risk, high-value application with an enthusiastic DevOps team for your first move. You don't start open-heart surgery while the patient is running a marathon.
Well said.
Then we tackled the downtime dilemma. We broke down the physics of data gravity to understand why zero downtime is a myth, and explored the massive architectural trade-offs like building complex, double-write microservices required to shrink that window. We walked through the five-step methodology, specifically highlighting the real-world traps of proof of concepts that don't mirror production, and the absolute necessity of testing your fallback plan before the draining phase of the cutover.
Because if the new cloud environment fails, you need muscle memory on how to point the application back to safety.
Exactly. We then explored the triad of testing. We saw how unit tests validate internal logic, how integration tests validate complex cloud networking and IAM permissions, and how regression tests are critical for establishing performance baselines against legacy systems. From there, we got into the trenches with migration tactics. We looked at the brute force reality of lift and shift using AMIs and VMDKs. We mapped out a weekend timeline of using differential backups to cheat data gravity, and we explored the network plumbing of using Cloud SQL as an external server to silently replicate an on-premises master through a VPN tunnel.
Which is one of my favorite tactics.
That's brilliant. Then we analyzed the strict rules of the database migration service for PostgreSQL. We learned how CDC tools actually read wall files, and why PickLogical is required as a translator. And we learned that DMS ignoring tables without primary keys isn't a bug. It's a critical mathematical safety mechanism to prevent data corruption when they're streaming updates. And finally, we stared into the abyss of planetary scale with Cloud Spanner. 6 exabytes of data, 2 billion requests a second. And we learned that surviving that scale requires a total paradigm shift, stripping the database of its internal business logic and refactoring your architecture to put the brain back into the application layer.
It is a phenomenal evolution of how we think about data storage and distributed systems.
It really is. And as we wrap up, I want to leave you, the listener, with a final, somewhat provocative thought based on our deep dive into Spanner.
Ooh, I like this. If the future of globally scalable cloud-native architecture requires stripping databases of their internal intelligence, removing triggers, stored procedures, and complex validation, are we eventually moving toward a world where the database layer becomes entirely dumb? Will it exist solely as a lightning-fast, globally synchronized storage fabric? And if so, as artificial intelligence becomes more integrated into our application layers, will AI eventually be responsible for dynamically writing, testing, and enforcing all those complex data integrity rules in real time, completely outside the database?
And if that happens, how does that fundamentally change the role of the database engineer? Do they evolve into distributed application architects, or do they become pure infrastructure and latency tuners, managing the physics of the data while AI manages the logic? It's something heavy to mull over as you head into your architecture reviews and certification exams this week. Thank you so much for joining us on this deep dive. Keep questioning the unseen mechanics behind the apps you use every day. Keep digging into the architecture, and we will see you on the next one.